We are Ariel Munoz and Emily Hunting for Lab 11 diffraction of 388. Our setup included a collimated laser light 74 centimeters away from an aperture, followed by a lens, and then followed by a camera at a variable distance. Using this setup, we observed the Fresnel and Fraunhofer diffraction regions. We use the Fresnel number equation to calculate the Fraunhofer distance. We calculated it to be a really large number, but the lens behind the aperture allowed us to reduce that distance.
These images show that for narrower slit widths, the Fraunhofer diffraction pattern is broader. These are the corresponding intensity profiles for the previous images. These are images of the Fresnel diffraction region, which is closer to the aperture than the Fraunhofer diffraction region for various single slit widths. And here are the corresponding profiles for the Fresnel region. For the Fraunhofer region with the double slit, the diffraction pattern gets more complex. There's a sinc function envelope around a sinusoidal smaller function.
Yeah, it's fine.
More profile plots. Here's the Fresnel diffraction for double slit and the profile.
We also observed the diffraction pattern of a circle, square, and triangle aperture. Here we measured the Fraunhofer diffraction pattern of a 200 by 400 micron rectangular slit by capturing its image and using a MATLAB program. In MATLAB, we normalized the graphs and then made the sinc function match the data. Using the graph, we calculated that I over I naught is 0.04329 for the first maxima and 0.0466 for the second. This gave us percent errors of 3.8% and 8.4% respectively. We then repeated this with a 500 micron circular aperture and manipulating the sombrero function instead. These are our results.
To find the distance at which you can resolve 2 point sources, in this case headlights on a car, we use this equation which gives you the minimum angular separation of 2 point sources, theta. This equation comes from the Airy function. It is the distance between the maximum and the first minimum. Using the value theta and the distance between the car headlights and simple trigonometry, you can find the distance that the car must be at to resolve the headlights. Then I plugged in the diameter of your pupil at night and the wavelength that your eye is most sensitive to at night to find that the car would be about 14 miles away at which you can first resolve the headlights.
This is what it looks like going from Fraunhofer to Fresnel.